Hello, sir. I'm Arjit Paldeep from the Department of CSE, and this is the presentation based on our final term assignment of the course Digital Logic and Circuits. We were assigned four tasks to complete this assignment. All the tasks were based on this circuit diagram, which is basically a digital parking system. Here we took input from the keypad, which is the maximum capacity of our parking system, which is by the way determined by our student ID, so that the capacity is almost unique for everyone. Then we also had record of the exiting and entering cars, and counted the currently available cars in the parking system and stored that information in the counter. Then we sent the current count to the comparator and compared that with the maximum number of cars we can accommodate in our system. Then based on the comparator's decision, we blink two lights, but one at a time. If the if the count of cars has reached the maximum capacity, then it shows full, and if it is not the case, then the timer circuit 2 blinks space available lights. It's both signboards are 7 segment display. So to solve the circuits, we have to keep in mind that the maximum capacity, we have that information by our student ID, but to count the exiting and entering cars, we must have an up down counter, which is possible to make by using synchronous counting systems. So uh, in a synchronous counter, we use JK flip-flops, and as the maximum capacity got by my student ID, it was 13. So to represent the number 13, the maximum capacity, we need 4 bits. So our counter is a 4-bit up down synchronous counter. So yeah, so in task 1, first I drew the block diagram and flow diagram for the above circuit diagram. Here are these. This is the block diagram, and this is the flow diagram. Here the entry sensor is responsible for counting the cars which are entering and passing the information to the counter. So then if the counter gets a signal from the entry sensor, then it counts upwards. Like if the previous count was 1, then it becomes 2. On the other hand, if the exit sensor uh, gives a signal to the counter, then the counter count decreases. Like if the previous count was 2, then it becomes 1 in the next iteration. And the keypad is responsible for the input of the maximum capacity of our system, which is we are getting from our student ID. So both of the inputs B and A are getting passed to the comparator, and the comparator gives the decision if A is greater than B. If A is greater than B, then we show space available, and if it's not the case, then we show the system is full. uh, Also in the block diagram, we have said the same thing. The exit sensor and entering sensor gives the information to the counter, keypad gives the information to the encoder, and the both of them then passes their informations to the registers, and the registers pass their values to the comparator, and comparator gives the decisions. uh, from the circuit diagram here, we can see there are two timer circuits, timer circuit 1 and timer circuit 2. uh, in the diagram as well, we have two timer circuits, timer circuit 1 and timer circuit 2, and both of them control their different 7 segment displays, and both of them show their text differently. Then in task 1 later, we were asked to show the internal architecture of the counter. So uh, previously mentioned that to achieve this, we have to we have to have a 4-bit up down synchronous counter. So for that, we first drew the state diagram for the synchronous counter. Then we created a state table called next state table. Here, y is the decision if um, the counter should go up or down. Here for this section, y is 0, which means if y is 0, then the count will go down, and this next lines or blocks are the decisions that current if uh, the counter has the current state which is shown in this block, then the next state will be below this. And if y is passed as 1, like the car is entering, and it should now behave as a up counter, then the outputs will be the following. So we got the truth table. Then we drew 16 k maps, 8 for the up count, and the rest 8 are for down counts. So 8 and 8 makes 16. Then we got the Boolean equations for the 4 JK flip-flops, but here we can see for Y we have one equation for J0, and for Y equals to 0 we have another equation for J0. Coincidentally, both of them are same, but for other values like um, K3 maybe, here K3 is uh, K2, K0, but when Y is equals to 0, K3 is some other value. So we wrote the equations here again. Then what we did is we took 6 multiplexers, and as inputs, as selection pin we passed Y, and in inputs we gave two values, J0 for y equals to 1 and J0 for y equals to 0. Likewise, um, we had another multiplexer where k naught equals to 1 for y equals to 1, and k naught equals to 1 where y equals to 0. So when the y is 0, then both of them will pass d0 and d0. So the counter will get the y equals to 0's decision 1 and 1. Sorry, we were calculating for j1, sorry. So we would be putting these values. So k, so here we have this this multiplexer represents the the upper left multiplexer represents the J1 input. Here we passed Y as selection pin, and D1 is the preferred input for when Y equals to 1. So we had this here, and when y equals to 0, we put J1 equals to Q naught hat, Q naught bar, and Q2 or Q3. So it's set to D0, and when y equals to 1, D1 is passed, and when y equals to 0, D naught is passed. So we can achieve this duality using multiplexers. So we pass the output to the J1K1 flip-flop. So our job is done here. Similarly, we did the same thing with the K1 block, and the same thing happened for all the rest of the multiplexers. So this is how we achieved a mode 14 synchronous up-down counter. In the second task, we were asked to design a circuit to for the two timer circuits. So from block diagram, from the flow diagram, we had the decision that if A is greater than B, uh, then show space available, or which means the timer circuit 2 is activated. Whereas when the case is not that, then the timer circuit 1 gets activated. We did the same thing here. In task 2, we when A is less than B, or when A is greater than B, then the uh, monostable timer gets activated. So we show the writing full with no blinking, and when it's not the case, that means A is less than B or A equals to B, then the astable timer circuit gets activated. And here we can see we have used 1.2 kilo ohms and 50 microfarads. So how do you come to these values? These were not given, right? So we got the value from our maths. So P is achieved from our student ID, and A, B, D, E, G all corresponds to some digits of our student IDs, and we get to 50%. Then D equals to 100 minus P, so D equals to ultimately 50. Then the frequency is also calculated likewise, so we got the frequency 12 Hertz. So as we know, T means time period. Period is reciprocal to frequency, so T equals to 0.083 seconds, which is also equal to 83 milliseconds. So as we know, TH equals to duty cycle times period, which means it is 41.5 milliseconds. So as we know, TH and TL in total makes T, so TL equals to T minus TH. So ultimately TL is also equals to 41.5 milliseconds. So for duty cycle, when duty cycle is 50%, the formula is this for two resistors. And by two resistors, I mean the calculation is for the astable circuit, and R1 and R2 are the corresponding resistors. So by solving basic maths, I get that R1 equals to R2. Then we were given three options for the capacitors. One was 50 microfarad, one was 250 microfarad, and the other one was 470 microfarad. So we checked all three of them and all three combinations. So for C equals to 50 microfarad, we got R2 equals to 1.2 kilo ohm, and as we have came to the conclusion that R1 equals to R2, then R1 is also equals to 1.2 kilo ohm. Then when C equals to 250 microfarad, then R2 is equals to 240 ohms. So R1 is 240 ohm as well. Again, when C is equals to 470 microfarad, then R2 equals to 127.4 ohm. And similarly, R1 is also equals to 127 ohm. Uh, Here, for as we know, the current flow is reciprocal or inversely proportional to the resistance R. So as we take lower resistance, the current flow will be higher. So if I take the lowest value of the resistors, then I will get the maximum of the current flow, which also may damage the circuit. So our preference should be to use the maximum resistance load we have in our hands. So I have 1.2 kilo ohms if I use the 50 microfarad capacitor. So we came to the decision that we will be using the 50 microfarad capacitor, and R1 and R2 equals to 1.2 kilo ohms. And again, this is our timer circuit diagrams, and from the inner side the timer circuit, each of the timer circuits looks like this. In task 3, uh, we were given a set of instructions that from the previous math, if we get th greater than 4, then for this math only we can set th equals to 4, and if TL is greater than 4, then we should set TL equals to 4. And as we have seen, both of those conditions apply for our math task 3, so we have set both of them to 4, and we were set to design an FSM to give an output as mentioned. So the outputs are A and B, and the clock period is 1 second, and we should show A for ultimately 4 milliseconds and B for ultimately 4 milliseconds. So we drew the state diagram for the FSM, which is this. At first it starts with A because we assumed that the inner components are set to 0 initially, and for next four states 0 0 0 0 0 1 0 1 0 and 0 1 1, it outputs A, and for the rest of the four conditions the output should be B. So from the state diagram we created a state table where we have shown the same thing. When the current state is equals to 0 0 0, then the output is 1. The output is A. When it is 0 0 1, the output is also A. The only change happens when the Q2 becomes 1, so it is no more A, it becomes B, and the rest of the states are carried out. So from the state table we created the following HDL code, where the inputs are input is the clock, because we are updating the values in each clock pulse. Then we are outputting where A and B, because we were told that we just have to consider A and B as outputs. So in the module we assigned three registers P, named P, to store the three present states. Then we created a variable named n, which is of type wire, which also stores three values for the next three states. Then we assign n0 equals to not p0, n1 equals to p0 XOR p1, and uh, n2 equals to uh, p2 and p1, or p1 and p0, or p0 and p2. Then we have mentioned that the code is always executed when the the code is only executed when it is positive edge of the clock pulse. So when the code gets positive edge of clock pulse, then it reassigns the present state to the reassigns the next state to the present states, and the next states now becomes the present state, and the loops goes on. And we assign A as not p2 and assign B as p2. All the equations were generated from this state table, which is so simple because we just can see these two outputs from this table, because A is only 1 with q2 when q2 is 0, and B is only 1 when q2 equals to 1. So this is what I have written: A equals to not p2 and B equals to p2. So, and for task 4 we were asked to identify the limitations of the given circuit and suggest some improvements to it. So the first problem I the first limitation I identified is the frequency of the blinking lights are fixed. So if if we add a potentiometer to the register line in the 555 timer, then we can control the frequency of the timer's output. So we can also control the frequency of the blinking lights. The second limitations I identified is the system doesn't show the current car count. So the beneficiaries or the drivers who come to the system do not know how many cars exactly are in the system. So they might be thinking that if we have only three spots and two cars are already in the parking system, and the driver is not as professional as he needs to be to park between the two cars, then he might not decide to go into the system. So it uh, sh- the system should show the current car counts. The next problem I identified is that we can currently count only up to 15 cars, because we are using 4 bit counters. But if we can increase the number of bits used in the counter, we can also count more number of cars, and the system is more scalable then. So more drivers can use the system and be benefited from it. So that's all from me. That was my presentation. Thank you, sir, for listening to the presentation. Thank you so much.